You know, it's been so funny. My wife took a photograph of me yesterday doing the Zoom chat. It's the most bizarre thing I think I've ever seen. Because there I am having this intense conversation and it's just me looking at my computer. I thought it was so strange.
Well, I used to like it at the end, like when you worked all night and you switched off the computer, and because the screen's shiny, you saw your own reflection alone in the room. It's kind of pathetically tragic, you know.
It's just the same idea. It's actually so fascinating.
Yeah,
you know, I don't know how that works.
It's been like that. It's been like that for a long time.
Yeah. So in the past, like the occasional telecom is fine, and like if you have them overseas, like if the important part is over, you turn off the sound, you turn off the video, get yourself a beer, and you just sort of watch it.
Yeah.
But it's so constant now. It's just,
very strange time. Very strange. I mean, I think we'll look back on this and wonder if it was real, the whole thing, you know? All right. Excellent. So yes, good evening. Before I do anything, I would like to just acknowledge that I am privileged enough to be doing this broadcast from my studio in Maroubra, which happens to be on Gadigal country, which is the part of the Eora Nation. So I just want to acknowledge that, and also acknowledge the fact that you know, members of that of those communities were our first artists and scientists. So it's with that spirit that I would like to sort of continue this conversation. So I should introduce myself first. So my name is Steven Durbach, aka Sid Sledge, and I am hosting the series of conversations between artists and scientists, and it's all part of National Science Week, and it's been sponsored by Inspiring Australia, so I'd like to acknowledge their role in this. And just to give you a bit of background about who I am. Well, first of all, I'm facilitating this conversation, but as my wife says, I'm a terrible facilitator, and I really want to just be part of the conversation. So I will be facilitating and also just really, hopefully, part of the conversation. And conversation I'm very excited about and looking forward to. But just so you know who I am, I trained as a scientist, specifically in the field of genetics, and I became a bit disillusioned with science. So then I decided just to call myself an artist, you know, and then have been working in that area for the last 10, 12 years now. But and wanting really to forget completely about science. But a strange thing happened about 6 years ago. I just stumbled back into science and realized, actually through art, how much I loved science and how beautiful the ideas were that science was dealing with. But it was interesting that I needed that filter of art to bring me back to that original feeling that I had about science. So I thought that was really interesting from my experience. And then I became a bit evangelical about wanting to work with scientists. So I spent the next few years from about 2016, 2015 working with scientists. And Professor Sven Rogge was one of my early victims, where I did a collaboration with the Center for Quantum Computation and Communication Technologies. And I must say, Sven gave me a lot of his time explaining some of the rather complex and intriguing ideas of quantum mechanics. And I'm forever grateful to you for that, Sven. So, you know, look, I'll just put this in a sort of context. You know, there is this history of art and science, but it's sort of like in the 20th century, has been stamped by this famous essay written in 1915. Well, it was a Reed lecture by C.P. Snow, where he lamented the alienation of art from science. And, you know, saying that these are two very important cultural elements in our society, and they should be engaging with each other more and not openly hostile to each other, was really the gist of it. But I would suggest that it's probably a lot more nuanced than that, because if you really look back over, and I'm only going to really consider Australia from this point of view, there is a lot of interaction between artists and scientists, and Australia is actually, I think, and you know, Paul can certainly comment on this, Professor Paul Thomas, who I'll introduce in a moment. There's been quite a lot of interaction between artists and scientists in Australia. And just to name a few people, Janet Lawrence, Chris Henschke, Sarah Jane Moore, and of course, Paul Thomas. There's fantastic institutions that are dealing with that interface. For example, Symbiottica in Western Australia, and I know Paul has done some work there. And some innovative organizations that are funding projects where artists can just go into science spaces and explore ideas. For example, the Australian Network of Art and Technology have got a fantastic program. Cultured Work in Piermont here in Sydney foster strong collaborations between artists and scientists, the scientists. So tonight, let's move on to tonight. And tonight is really about the world of quantum physics. Now, that's a really interesting place to explore, I think, for artists, because if you think about it, most of our experience about who we are and where we fit in the world comes from because we live in amongst it. We develop an intuition for it. Now, with quantum physics, so a feel, we get some kind of feel for this, but with quantum physics, it's never been accessible, at least to our conscious experience. So we don't necessarily have an intuitive feel. And I think a lot of the popular culture around popular myths or analogies for quantum physics feel like they're not quite hitting the mark. So it's a really interesting place for science to engage. And just to give a little bit of historical perspective, you know, when quantum physics was first sort of came to the fore, that was during the era and where philosophers like, I think it's Ernst Mach was very prominent, one of the positivists, and they really felt quite strongly that you shouldn't rely on things like intuition and feel and metaphysical illusions. It was all about empirical data. That's where your only sort of truth should come from, was through that empirical data. So that, and that possibly has had quite a big influence on the way we move forward, where ideas around feeling and intuition have really been not that well integrated into quantum physics. It's a great science because it predicts really well, but what does it actually mean? Like, it's got some really complex questions that are asked, but we don't necessarily know what it means. It's another world. We call it the quantum world. We live in the classical world. How do we know that world? And I'm really hoping that tonight's conversation sheds some light on that. So I'm now going to introduce the panelists, and I'm deeply honored to have both of these men here. Professor Sven Rogge, he's one of the principal scientists at the Center for Quantum Computation and Communication Technologies, also the head of School of Physics. And as I said, he's given me much of his time in the past, and I'm really delighted to have him here today, where he will talk about his experience with quantum physics. And also Professor Paul Thomas, who's been very instrumental for quite some time doing interdisciplinary, transdisciplinary research in the arts, looking into different disciplines. For example, he's the director of the Studio for Transdisciplinary Research, and he's also developed quite a few conferences around bringing artists and scientists together. And he's done some fascinating work actually working with quantum physics data to help us navigate into that world. So I think I've spoken enough initially, so I'd like to really invite, welcome first of all, thank you for joining us, and also to our attendees. It is amazing that you've taken the time on a Saturday night. Well, I know we can't go out and boogie anymore and do all that kind of thing. So now we sit on a Saturday night listening to quantum mechanics, quantum physicists and artists talking about that interface. So if you have any questions, we'd love to hear from you. Join us in this conversation. It's amazing to know you're out there. And I'd like to just welcome Sven initially. Maybe you can tell us a little bit about, tap into a bit what quantum mechanics actually means. What is it?
Sure. First of all, pleasure to be here. Look forward to that conversation. So quantum mechanics. So quantum mechanics is the theory that basically governs the behavior of atoms. It's, as you said, not classical. It's not the throwing a ball or the apple that drops off a tree. Classical mechanics is deterministic. If you know the initial conditions, you know the laws of physics, you know exactly what an outcome of an experiment is. In quantum mechanics, that's not the case. Quantum mechanics is probabilistic. You, for example, look at electron motion, like in how the electron goes around an atom, or what the spin degree of freedom of an atom is. And even so, you set up the experiment a couple times exactly the same way. You carry out the experiment. You will not always get the same outcome because it's a probabilistic nature of quantum mechanics. You will, on average, get the same outcome. For example, if you have an electron go a certain path, it can interfere with itself. So if you measure, you can sometimes find it left and sometimes find it right. If you measure many times, you always find the same distribution, but you only measure once. Basically, that doesn't tell you anything. So that's the probabilistic nature, and you briefly mentioned intuition, since our day-to-day life doesn't behave that way, it's really hard to develop intuition. Intuition is very important. That's why quantum mechanics is such a challenge. At the same time, it also presents a huge opportunity because if you can actually harness and preserve the quantum nature of a state, then you can also utilize that to carry out calculations with that. And if you build a large enough systems, they're extremely powerful because like quantum computation is a totally new concept of processing information that's very different than the classical way. And it's inherently parallel. Basically, what you build up is systems like the electron around an atom. It's not at one specific point, it's everywhere at the same time. So you basically also use this kind of phenomenon where like a quantum state basically extends over a large range, and you have all the interactions that give you, first of all, a very large volume for the information, and also a highly parallel way to process that. So that for specific problems, it's not universal. For specific problems, that allows you to solve certain problems much more efficient than you can do with classical hardware. We're now at a very exciting time where this becomes practically possible. We can carry out experiments in that space. Because the challenge is this quantum nature is extremely fragile. So like any interaction for a prolonged period with the environment makes everything classical again. Right? So it's really hard to basically preserve that quantum nature and then utilize that. You asked me, I should briefly say what I do. So I'm an experimentalist. So I probe nature, I probe quantum systems. And what I focus on is how these quantum systems interact with each other and how they interact with the environment. So on the one hand, we want to build larger systems, so we have to make sure they can interact properly with each other. On the other side, there is the challenge that if they're too exposed to the environment, that they become classical, right? But of course, you want to work with them, so there needs to be some exposure to the environment. That's the kind of thing I focused on.
You, as the observer, are you the environment in this space?
Yes.
Okay. So it can never be left. So you can never leave the quantum system alone. You always have to make an observation.
Exactly.
If you want to know anything about it.
If you want to process information, there's always a give and take. You have to prepare and you have to extract, and you have to do that in a specific way to still basically maintain the quantum information.
Okay, well, that's an interesting place then for an artist to explore, because that's all about the ideas of those, I guess, are words that words like fragility and uncertainty and measurements is I guess a strong scientific word, but all those other words are quite are words that are, I don't know, Paul, does that ring true, that those are words that are more comfortable in the place of an artist, or is that an old-fashioned notion of what it means to be an artist? I think you're on mute, Paul.
No, I was just leaning forward as an uncomfortable position to switch the mic on. It's incredibly complex, but from my perspective, quantum physics and the uncertainty is very similar to the practice of art. We're trying to capture a kind of reality, not let's say a physical reality, but a reality of an idea or something, and we're trying to capture it in the kind of act of happening. And sometimes quantum physics is trying to do the same thing. They're trying to prove, like Bell tried to prove or disprove the theory of quantum mechanics, So they're setting these things up, and then it becomes based on the probability. And every time you make a mark, let's say as an artist on a piece of paper, it's a probability. You're summing up all the possibilities that there are, and you end up with making one mark. So it goes from maybe from a quantum state to a classical state with the mark, because you collapse all the possibilities. So art's been doing this for a long time, and with measurement, we can go way back, to the early 19. When Duchamp in about 1917 did the standard 3 stoppages, when he questioned measurements by dropping a piece of string. But this was based on things that they'd read about mathematicians and this, not being able to define an actual measurement. so that they predate certain things that happen, and artists are running parallel, inquiring about it, but within a different set of parameters. So, you know, they're not necessarily trying to make it quantifiable, but more qualitative.
So I mean, so is there a qualitative aspect to what you do, Sven? I mean, I'm trying to understand what you mean by qualitative. I mean, you know, what is that? What is that? I mean, your work is all about measurement.
Yeah, definitely. So it is, of course, true that at the end of the day, the empirical result is what counts. But the way we get there and the way we progress and further understand, that is not like a brute force pathway, because brute force is just too slow. So that there is basically the getting a picture, getting an understanding, building something in your head. And if I would be a better artist, I would like to express it also on canvas. Like getting sort of your interpretation of what you think is going on, being creative, thinking about how a system could behave. And then comes basically the experimental measurement side. Then you set up an experiment, you test something, you see if your intuition was correct, you refine your intuition, you take the next step. And there was a time where people said, like a scientist should not assume, right? And should just measure. But if you just basically start measuring everything, you don't move forward, right? You have to have a picture, you have to sort of get a mental image, and then from that, be creative, try something else, and move this in a direction that you want to go in, right?
Because I guess all we have is metaphor. We only can, as a human, we have to have a picture in our head before we can do anything.
Yeah.
We're not instruments. Paul, do you want to tell us a bit about how you've got, like, your trajectory is really interesting, because when I first came across your work, you were interested in verandas, okay? And now, sometime later, you're working at the interface of actually using quantum data. Is there a, and I'm nervous to use the word logical, but is there a pathway that you followed that led you coherently? Maybe that's a good word, coherence, from verandas to working with actual quantum data. And then, can you want to tell us a bit about those experiments?
Okay, I'll just to start with then from that question. The question was really, I've always been fascinated by space, the space between us and the world around us, and you know, whether it's to do with perspectival space or whatever. But I always had a very strange relationship with verandas, and when I came to Australia, I didn't like verandas. I didn't like being on them. I didn't like being seen on them, and I didn't like seeing people from them. So they were kind of this very strange territory. And it followed on from a series of experiments of space that led me to the veranda. So the space of the veranda, between the private and the public, there's this strange fetishized space called a veranda. And if you just walk past verandas, you'll see what I mean by what people put on them as this representation of an other space. So if you then start to say, well, I became interested in that, and then I became interested in the space between buildings that are sort of left out of the equation, these small residual spaces that sometimes appear. And then I started to become interested in the space between us and our environment. So when I touch the camera, how much of me is part of the glass of the screen? And so I started doing experiments with nanotechnology to see how much of me became part of the world around me at a nano level. And then that led me to start to ask questions about the sort of nano level and where the space of atoms and the relationship between atomic matter. And it got me interested in this notion of where life exists. So where does life exist at a quantum level? So if you were to use the sort of philosophical thing of a bald man, when's a bald man, you know, how many hairs, if he has one hair, is he still bald? If he has two hairs, and so on and so forth. So if you said, the other way around, like if you took one hair away, would it be two hairs? So at what point is that point where there's the shift? And therefore within a cell, which we think of as part of a living thing, if you took one atom away, would it be, if you took two atoms away? So we start to talk about matter and life in the same kind of context. And physics started to use that as well. I mean, there's Max Tegmark, and he makes notions of consciousness in relationship to quantum physics. So I started to become very interested in that, amongst other things. And when I met Andrea Morello at the same institute at UNSW, he was using and developing a quantum computer using phosphorus and silicon, and using the phosphorus electron to spin the electron. And just the language of spin is so different from a physicist to my version of spin. But as you said, they use metaphors like a spinning top, like a child spinning top, to explain the spin. But it's not that spin. It's you know, like it's a strange way they use language that doesn't necessarily make sense for their world, to try and explain their world. And then people get the really wrong idea about what that world is, and maybe feel a bit safe because it's like a child's spinning top. Anyway, so then I went to, as I was working on it, and he was working on this, sending microwave signals to control the spin of an electron, doing these probabilistic experiments that Sven mentioned. And I really liked the idea, and I've been reading a lot about Feynman, who, you know, the sort of father of nanotechnology to some extent. And I thought that the microwave signal from an artistic point of view is fairly neutral. It does have no conceptual framework apart from being microwave. So I wanted to try and give the signal something. So as I was working on this quantum consciousness work, I asked if I could have my voice read to an electron. And I can show that to you now if you want, because we spoke about this. And then you can see what you guys make of this. And it might help the people looking to see something visual in relationship to what we're actually saying.
Great idea.
So this is from my website, so it's easy to find. It's just visiblespace.com. Hence, you can see all the chairs and verandas and that whole progress that I just mentioned. So this is really the data from the quantum computer to try and Sven could explain it maybe better than I could, trying to track the position of an electron once it's bombarded with these microwave signals. Let's say 200 signals at 5 milliseconds. So this is the sort of stuff that's happening, and I wanted to try and see if my voice could control it. So I wanted to read to it, but I wanted to read to it something that was relevant. And it seemed to me, if I read Richard Feynman's 1959 paper, can't remember now, about the beginning of the concept of a quantum computer. So if you want to deal with quantum things, you have to have a quantum computer, according to Feynman. And so I thought if I could read to the electron and read Feynman to it, it'd be like, you know, God talking to his son, you know, that kind of idea. So this is a little bit of the video of that. Sorry to jerk you around.
Mechanical laws. Or we can turn the other way and say, let the computer still be the same kind that we thought of before, a logical, universal automaton. Can we imitate this situation?
So
our only hope is that we're going to stimulate probabilities.
I'll
that
just
we're going
pause
to have
that.
our computer.
So you can, the blue is tracking my voice from the northern, and you can see how irregular it is and destabilized it is. And the other is a sort of more coherent signal of the green of the spin of the electron within this sort of phase space of the dome. So you're imagining like being in the center of there and pointing your finger to all these spaces around, and that is the potential for where the energy of the electron might appear.
And oh, sorry to interrupt, but can your voice, are you trying to see if your voice can interfere with the signal of the electron or communicate with it? Or what is your intention?
My intention is just to try and see if my voice can stimulate the electron to spin, you know, and therefore to maybe spin in different directions, because your voice is varying frequencies and so on and so forth. And it obviously has to be reduced down to a very small amount of time. So really it's indexical, I suppose, to my voice as opposed to really being my voice.
Yes.
But it's just the idea of this communication with it. When I first used an atomic force microscope, which uses touch rather than optics, and I was talking to the technician about scanning the skin cell, when I transferred the data to sound, you could hear my voice because I'd left the door open on the equipment. And so it's so sensitive that it has to have all this protection around it, so it doesn't, no noise can go into it and affect it. So this kind of experiment, which is full of noise cancelling equipment to try and get to the data, which potentially could be noise in itself, is, so I was really interested in just that physical thing of talking to the electron as a potential concept. And this data then drove the artwork for quantum consciousness, which is, you know, a bigger data projection piece.
And Sven, do you think like work of this type can inform something? You know, it's quite often that artists benefit, can really learn a lot from the scientific process. But one of the things I'm really interested in is how it informs, can inform the other way. I mean, can you get anything specific from seeing an artist's work, or is it a general shifting of the way, you know, of a consciousness or something? I mean, can you talk to that idea about how it might affect the work that you do?
Yeah, the artist expression of like a quantum mechanical reality, or like a probabilistic behavior, like the way an artist sees this and basically interprets that, that can sort of give me a way to see the system in a way that I have not seen before. Like maybe I share something just to sort of show how different my world at times is, and where I think I benefit a lot from artists. So this very mechanical display that you should see on your screen now, it's basically, we see a bunch of balls which are atoms. And we recently published some work where that electron spin that Paul talked about is actually directly coupled to the electron motion. And this is a drawing that my colleague, scientific colleague, Takashi Kobayashi, made, how he sort of envisioned how the motion of the electron and the spin are coupled, they're linked together, which on the one hand is an opportunity because that means we can do something with the spin based on the motion. But you see here in this image how limiting and rigid everything is, right? And as we talked about, quantum mechanics is not that rigid. Right, so like I would imagine that we could, in work with an artist, come up with a mental image, with a picture, with an interpretation that is possibly actually closer to the reality, and then would give me in exploring that like a new level of intuition that I can take back to the experiment, try some new ideas, and sort of refine the way how such a system interacts with its environment. Right. So even though to some degree this looks beautiful on a sort of Swiss watchmaker kind of level, it also, I think, shows you how limited like our way of visualizing or developing certain mental pictures are.
Yeah. Is quantum, I mean, just because that looks very tangible, you know? Right. I mean, when you think of a quantum system, the image do you have an image in your mind about what a quantum system looks like? Or
Yeah, good one. Like it actually, like in part of this work of trying to understand how quantum mechanical systems interact with each other, we actually image the electrons. Like we use like a scanning tunneling microscope, which is a similar microscope to what Paul just mentioned, to probe. In this case, it's not touch. It's basically sort of feeling the charge cloud. And what you see here in this image is this is not sort of theory plotted. This is actual measurement. This is the charge cloud of two electrons that interact with each other. So these are like in silicon. That's partly where these sort of rough bumpiness comes from. And so the way they interact, which is a very fragile thing, is like we measured this, and it gives me like an image of what that electron system looks like, and then allows me to think about like how could I try to engineer that system so it becomes more robust. But again, this is to some degree very limited, right? Because this is sort of the direct extraction of the data and then visualizing it in terms of height on the computer. There's not this extra level of abstraction that again would help, I think, to further evolve the intuition about the system.
So it's still too much of a classical representation, is what you is.
Yeah, that's right. That's right. Because I mean, obviously, the same way as my colleague Andrea Morello did the experiment of the electron basically moving in the Bloch sphere. That's not a single experiment. You basically have to carry many experiments out because you have to average. In this case, also, the electron is everywhere at the same time. What I do is I use a weak probe over a prolonged period to actually work out where the electron is on average, right? So I lose all that extra information, which we call the phase, that basically sort of has the true, like the ultimate quality of the quantum state. Like there's an extra whole dimension that I cannot extract, because the second I try to extract it, I would collapse the wave function. Right? So all I can do is basically look at the classical envelope of the whole thing. Right?
And Paul, how is this sort of seeing things like that, or dealing with actual quantum, how's it changed your perception of your classical world or your classical experience?
Well, it's the whole thing of the probability has changed, the way that I think a lot in relationship to notions of uncertainty, and which is kind of played out. It's almost as if this century was leading towards uncertainty, and we've hit uncertainty in a big way. And I think it's something that's trying to tell us quantum physics is to learn to live with uncertainty and to accept it, not to be scared of it and not to run away from it and so on. And because they're all, nearly all our lives are based on a certain sense of probability of certain things occurring. And but the interesting thing is I did a piece of artwork about that very thing that Sven was talking about, and I could show you my impression of that.
Yes, please.
Quite quickly. I could just share this with you. Sorry. So this is, I'll just play the video for you. I'll try and make it a little bit bigger on the screen so you can see it all. So if you just remember that this is an image of, it's a video of images that are broken up through a sine wave. And then they are actually being placed within that sphere that we spoke about. And they're trying to start to emulate a notion of an analogy to thought. So if this is part of the quantum computer, and if this is where the electron is firing, and you can see now I'm just turning it around manually to show you how it's firing within this. So it's actually using the data from the lab to make them fire in these positions. So if you think of this as the possibility of an idea, trying to capture it, like just analogous to, and that phosphorus is in your brain, so we've got phosphorus in our brain, so there's an analogy there. And we've also got Netflix as well. So this always comes up with these things, so I'll stop sharing that.
We could watch something.
Yeah, but what you get is this notion that I was thinking about this, and I was writing these stories then as well about quantum phenomena. And it seemed to me that if you've got phosphorus and we've got it in our brain, that maybe that we could be quantum. In other words, like quantum biology, but maybe we could be processing quantum things, like the birds use quantum to navigate, plants use it, quantum tunneling to transfer through photosynthesis, and so on. So we get this stuff happening. So it seemed to me that if we could do that, then we could start to say, well, this is similar to how thought takes place. And so the quantum computer is about a thinking machine, and we've got a thinking machine, and we're using the same atom, an electron, to do it. It just seems weird. It's bizarre. So it struck me that I should start, and so I started writing this story about a detective who got affected by a microwave signal and started to take on quantum properties. And then I found this physicist from America who wrote this paper saying, are we quantum computers or merely clever robots, was the title of the paper. So of course I downloaded it and read it as much as I could because it had formulas in it and stuff. But fundamentally what he was saying was that he'd done all this research about this very topic of the phosphorus and its stability, and because it's very fragile and because it's working in noise, but he tried to work out and re-engineer that could it be affected in the brain? In other words, could it be a physical thing? Could you use quantum in the brain? And he found the only atom that you could use to do this was phosphorus. And so you go, oh my God, I've been writing this down myself in my little cafe, you know, and there's this scientist who's saying the same thing as we're saying, but just in expanding the idea by visualizing it and trying to write it down as a sort of fictional novel. And this was really quite exciting. So I managed to get to meet him and talk to him and tell him about my detective and stuff. But it was just that once you start to think about these things, we have these sort of commonalities, that we're the same materiality that is being used, we're using, you see. And it's like graphite, you know, like we use a pencil to make our ideas visible through using it and we're 18% carbon, and the whole pencil is carbon, and the paper's carbon, and we're using all these same, and you go, wow, that's kind of cool that all these things are part of our material awareness.
Yeah.
I'm going on.
No, but it does feel like, you know, if there wasn't, I mean, if that it's almost like this free flow of information, you know, where you were able to engage with what a scientist were thinking. I mean, I guess if there wasn't any quantum physics, you wouldn't be having these thoughts. And
yeah, but I mean, you might be thinking them, but different ways. I mean, there's new materialism and all these other things that are starting to human, non-human relationships and so on that are starting to. But quantum gives you that. At the moment, I'm working on quantum chaos, which seems to me to be a really interesting way of looking at that border between a classical and a quantum world. You know, that's and the sort of data that's coming up, the speculative data, because I'm not sure that they can actually reproduce it, but the person that one of the students gave me some speculative data, the Hasumi data, and I've been using that to try and re-engineer an image from a classical image of chaos to a quantum image of chaos. And
maybe Sven, you could talk about your ideas on that, on quantum chaos.
Like,
and we can
listening to Paul. So for me, there is one common link, say, between quantum computing and biological systems like the brain, and that is, on the one hand, complexity. like very large complex systems. And in quantum computing, so the key element is that we're talking about collective behavior. It's not about one electron. Like one electron itself is boring. It's not powerful. It's basically, if you couple them together and you get the collective behavior of a large quantum system, that's where the inherent advantage lies, and it also makes it fragile. And in the brain, like one neuron is also absolutely useless. But the fact that you have a large number interconnected to them, like I'm not sure if there's quantum or not quantum, I'm not so sure there's quantum, but it's again, it's a very large complex system that gets its power from the complexity of a very large interconnection. And the same is again true with the quantum bits. The fact that it's not just like in a regular computer, bits where one influences the next one and the next one, they're all interconnected. You have to have like 50 of them. They're all interacting with each other constantly. It's one large interconnected system, right? So from my perspective, that's where the analogy and the challenge lies, to understand that. Yeah.
So it feels like in a weird way you're building an organism, you know? When
yeah,
it's,
absolutely. Yeah. Like the one organism, it's cold to some degree, it's dead. So it's a very different thing, but it's a fully interconnected, complex system that can actually do useful things. Yeah.
And Paul, I think that's what you were in that book, because I haven't finished reading it, I have to be honest, but I'm enjoying it. Ed Eats a Pork Pie. But that seemed to be where you're going, is that we are all interconnected on some level qubits.
Well,
is that fair to say?
Well, the potential is that we could maybe, if we were thinking about using our the brain, then how would it work? How would you actually then use the quantum potential that we possibly have? And then I started to think whether intuition was a quantum phenomena within the brain. So if you thought of quantum tunneling as happening, as a strange effect that allows energy, let's say in plants, to go from point A to point B without losing any energy, and it happened quicker than thought, because intuition would have to happen at a kind of infinite speed for it to be intuition. Otherwise, it would just be thought, if you see what I mean. So I was just trying to work out whether that was, but these are just speculative ideas that come about by writing, and people didn't know that, the quantum phenomena was part of nature at one time, but it seems obvious now. It seems obvious when we think, if you had a phenomenon like quantum, wouldn't nature use it? It's part of, so it's like maybe we're not, we're having intuition, but maybe we're not listening to it. And so it starts to, these things, and then how to try and translate that. So one thing I could say about the work I just showed you was that when I show it, I don't have any information that it comes from a quantum data. I just have that visual being presented, because I'm trying to develop an aesthetic experience that draws you into something as an artist, as opposed to a didactic kind of description of an event. And the same thing with trying to express quantum chaos. And as Sven said, if you're going to, a dynamic signature of quantum chaos it is entanglement. So if you can point an electron in that direction towards chaos, then it would, as far as I know, Sven could correct me on that, but this is, this seems, like how they're going to make an entangled array of electrons be affected by a microwave signal, by getting them to take a chaotic point of view and then bombard them, and then they would all be entangled and they'd all be communicating at the same time, and therefore you'd get maybe that strength. But again, that's just me speculating that that's what's happening.
Well, that's the idea, right? Is to speculate and
yeah. There's but I couldn't do any of the maths or other things to do it.
I think maybe what Paul just said, that brings us to the questioning that I think Gallia just
yes.
Like Paul says, he cannot do the math. So the question, if I read it out, is do you think art can contribute to science in terms of furthering the work being done by you and your team? And if so, how? So my take on that is, if we present our scientific findings and our interpretation of how a certain system works, and an artist, and I guess in collaboration with the scientific team, forms the artist's intuition and picture about that and expresses that. In that expression, I would expect there can be further insights that were not there before, even though the artist didn't do the math, but the artist basically paints or creates the artist impression image of what's going on. And I would expect that can then feed back into the science, basically stimulate the scientific intuition, the scientific ideas that were possibly not there before, that then can go back into the experiment and further our understanding. Right? So it's not something that I have done, but I find it very interesting and stimulating. And given how complex the systems we deal with, and also when we book progress by, of course, doing experiments and analyzing them, but a very core aspect of us booking progress is talking to our colleagues, bouncing ideas around, jointly building an image of what's actually happening, right? That's also why Zoom is such a drag, because we don't talk face to face that much anymore. So because this interaction is very important. And as we know, if you put more diverse backgrounds or ideas or patterns of thinking into such a process, you make bigger steps. You further you develop the system quicker than you would do if everyone's exactly on the same page and has exactly the same background. So that's how I could imagine that science and art could collaborate, with art bringing in a totally new perspective into this interpretation and visualization of the science.
Yeah, and there seems to be a growing trend where a lot of big grants now include a position for an artist. It's becoming a thing, I think.
I think that sometimes when the debate gets out of the lab and gets into an art gallery, it changes the context of the debate and other questions come up. And so I'm not, there's so many things to experience and express. To limit yourself to a binary between art and science, I think is problematic. I think that science does that maybe, and art does that sometimes. And the thing is something that, let's say, Sven might say to me, like one sentence, might be enough to trigger a whole body of work. I don't need to know Sven's life history. I don't need to have studied Sven. It's just that certain things capture you and drive you. And it could be, Sven could say when he was a student that a lecturer said something about physics to him and it just went bam in his head and he just went, wow. Like I would say that you could take a line from a poem without knowing the whole history of the poet. You could take something from Deleuze's philosophy on the fold and go, oh my God, the fold is just an incredible concept. But I don't need to know the whole history of philosophy. As an artist, I can let all these things affect me and affect how I produce a work. And that's what I think is exciting, is, that I'm not restricted to some extent, because nobody's going to fund me to talk to an electron. Really, it's difficult to try and engage science with that as well, because it seems too speculative, and they might, lose some funding.
I think that. Sorry, carry on, Paul.
But I was just going to say the beauty of it is, as Sven said at the beginning, is that science seems to, through physics and through the probability, seem to be embracing more the fact that you have to intuit the topic because you can't understand it. It's just not understandable to some extent. And no matter how hard you try, but you can kind of understand it in a bigger sense. It could be here, it could be there, but then it's this energy. And if you think about it, rather than a ball, if you think about it as a smear or a smudge, it starts to feel that it could be in any, and each one. And so I've been working with felt, you know, the stuff that felt before it, as an idea for classical chaos, because, you know, it has all, like when you do pilling off your jumper and pull it, and it's the sort of stuff that if you pressed it together would become felt, and trying to rearrange that into chaos, into quantum chaos, and seeing how the patterns are formed from using the data to sort every pixel in the image based on quantum chaos speculative data. So you're actually rearranging the whole image.
Yeah.
And it comes out quite almost in a strange way mechanical, if you see what I mean. There's I can show you quickly just because I know you're running out of time. But
I guess while you're looking for the image, I mean, that is the joy of it in a way, the art. You get to ask slightly absurd questions, but then you hope those bring you back to something that's really interesting. And I mean, that could be something interesting that art brings to science is.
Yeah, I mean, if we just, I mean, we find it perfectly natural that we talk to a chemistry colleague to get a different point of view to a problem. Like talking to an artist, I would put that in the same box, right? It gives you a different perspective with a totally different background. And as Paul said, you don't have to be the person, you don't have to have the same background. It's you trying to understand what the person says, your interpretation and your next question or comment that keeps the ball basically, or kicks the ball off rolling and creates ideas that weren't there before.
Yeah.
So this, what I just showed you was the first image was the felt. So sorry, so this image here that I showed you is then animated by the computer on a sorting algorithm, and the sorting algorithm then starts to produce at the beginning. You can see that it's sorting the information, so it's taking every pixel and sorting it, and then it starts to, towards the end of its sort, it's created this. Now this again is a multiple of the image, but this is what happened from the data. And so then you could read into this as a way of, let's say, talking about the fact that that pattern is like something that could be read by a computer if it happened, and then that would be the data that the computer would get from it from processing. So it's like a way of thinking about processing the information, but hopefully it gives a really beautiful image. And so after that, I'm not, you know, this is where I'm interested in that. I'm interested in the aesthetics. So how can the aesthetics, and if anybody looks at an artist, can look on, who's listening, who can look on the internet, but look at Roberta Matta in 1944, making paintings as a surrealist about what appears to be quantum phenomena, then you think, this trying to visualize the invisible, the intangible, is a beautiful thing to try and do.
Yeah.
I think from a science perspective, there's also, at least I am, and I think many of my colleagues are, the firm belief that nature is beautiful. So you always try to understand and unravel and find the next level of understanding, of seeing something that just seems to make sense and is beautiful. Right? I mean, quantum mechanics at first may not look like that because it's probabilistic, it's noise, right? But of course it isn't, right? There's underlying structure that again is beautiful, right? So I think there's with very different tools, there's sort of an underlying urge to discover something new, beautiful, right, and help create it. Of course, it's there, but create the understanding, the knowledge about that.
Yeah, absolutely.
Yeah, it's an interesting thing when you're driven by that need to find something beautiful. I mean, I always think back to the DNA molecule. It's just mind blowing that it happened to look like that. It happened to be this extraordinary pattern, and it could have just been like chaos. It could have just been a jumble of, but it wasn't. It was this extraordinary double helix. You know, I mean, you encounter that, you think that's just almost too good to be true.
But I was at a talk the other day and about the black hole, and it was really interesting. Chris Hensky was speaking at it, and I was listening to the person who was doing the imaging of this black hole, you know, and there were two ways of imaging this, and the one that she was doing was called forward modeling, and it was regularized maximum likelihood, and to me that was just incredible. You know, like, I've done a painting which is a regularized maximum likelihood of what reality could be like, you know. I mean, and then you've got the notion of the machine. So is it the machine that's the observer here, or the person who's observing the image that's coming down? So is it the interpretation of the data by the machine? Because these are numbers that aren't conscious perception, you know, the perception of a conscious person. They're the construction of a machine who has, you know, who's got a single eye most likely, or two radio telescopes somewhere in the world that are trying to create a stereo type of image of the black hole. So I think these are really interesting questions about how we see and capture the world. And I just think, you know, like I was thinking that notion of quantum annealing is something I've been looking at, which is, again, the probability of finding the lowest point and writing this software that would work at that level. And I really used to love the sort of delayed choice quantum erasure, where you measure something affects the measurement, and if you delay it long enough, then according to some physicists, because I don't think you ever get one agreeing with another, the photons, the waves turn into photons but go backwards to come back through. So it's like in that point time goes backwards, and they have, you know, they have the counterfactual definitiveness. I mean, who could come up with counterfactual definitiveness? I mean, it's such a cool title. You think, you know, if art came up with it, would it be thrown out? You know, my drawing is counterfactual, so it's every mark that I didn't make to make the drawing, which you can't see because I didn't make it, because it's every mark I would have made. Only physics can do that and get away with it.
Negative space.
Yeah, and you go, yeah, just look at the beautiful the paper was, you know. You go, but so I get it, but I mean, it's so much like, I mean, delayed choice quantum erasure is the same as making a mark on a piece of paper. You know, it's just, it really is. You know, you have to do all these processes, and then it happens and it goes back, and you then have to make the second mark which justifies the first mark, and so on and so forth. And you're trying to capture reality with a piece of graphite on a white two-dimensional surface. I mean, it's really complex, and you're using your brain, which is lying to you all the time about the world anyway. And it's like, I mean, it's upside down, it's this, and my eyes are flickering, and here I am trying to do all this stuff. And, you know, and then but so it takes time to build up a relationship with a scientist who wants to work in that way, because they're not time rich sometimes, scientists, and they've got a lot of pressure on them, and they're always trying to do something new. And although art wants to do something new, it realizes that there really isn't a lot new sometimes that it can do, except it can just try to be honest or truthful, even though they know that they can't be truthful, because we don't know what the truth is. But it's that attempt to get there that you're looking for. And I think that's where science and art also meet, is this an attempt to try, and we're not trying to do it in a qualitative measurement way, we're trying to do it maybe as a qualitative way.
I almost don't want to say anything else, because that's such a great way to actually conclude this. But I have to just quickly ask, Sven, so thanks for that, Paul. I mean, if you reset the clock of physics and get back to this time, do you think you'd arrive at the same picture, or is there like other pictures which are so vastly different from the one that you have now, which are also correct, or correct in the observational, or in the measure, in the way the system is all measured?
You mean if we would revisit, like relive the last 100 years?
Yeah, I just get new, different kinds of instruments, or different models, or different theories, and still arrive at a measurable thing. that accords with what you measure, but is a completely different story, or the other way around.
I could imagine that the way we discover science could take a different path. The outcome would be the same because it's the same universe we live in.
The same universe.
Same physical laws.
I guess that's what I'm asking.
Quantum mechanics had a very sort of burst-like development. There was this whole like creation in like the 20s and 30s, and then sort of puttered along. That it was another sort of like the Bell equality suddenly happened, and that was an epiphany. And then it sort of puttered along for a while, and then maybe in the late 90s, the ideas came up to actually use these systems and do something with it. Right. So I think those timelines, they could drastically change, but the outcomes would be the same, right? There may be things that the alternative timeline would have known by now that we don't, but on the other hand, they would have missed others, right? So it's that quest for scientists, society to understand the world we live in and try to do something with it. That is limited by us, of course, us absorbing it.
So this intangible world is tangible enough that we will just rediscover it again, even though it's so hard to get a hold of. You'd still discover the same intangible thing. And that's where we're going to leave it. Thank you, everyone, for attending, for visiting us. And I just really want to say thank you, Paul and Sven, for your time. And just, you know, for me, it's like I think for me, it's quite a sacred thing, you know, like here we are in such different worlds, but, you know, we're taking the time to spend time hearing each other's points of view, sharing each other's experience, and possibly knowing that we'll never quite, you know, but we're going to always, and maybe it's, as you said, Paul, we'll always try and build up this image of what's out there. And I think that's just maybe what it's about, you know. And so I just want to thank you both for joining me tonight. And yes, I look forward to many more conversations, and everyone else who joined us out there. Thank you.
Great pleasure. Thank you.
Good night.
My
Good night.
pleasure.
Have a good night.
Bye.
Good night,
Bye.
everyone. Bye-bye.